All right, good afternoon. Welcome to our afternoon colloquium. It's my pleasure to introduce our speaker for the day, Dr. Ardavan Oskooi. And I would like to start by a brief introduction. He has a very diverse background. He got his undergraduate degree in engineering science from University of Toronto in Canada, and then he moved on to MIT. He got his master's and DSc degrees at MIT under the supervision of professors Stephen Johnson and John Joannopoulos in the area of computation and design of nanophotonics. Thereafter, he went to Kyoto University to do his postdoc for about 3 years, I believe, and post that, actually that included a stint at University of Michigan as well, I should mention. And post that, I think he returned to the United States, and he has set up a startup company in San Francisco area called Simpetus, and it's trying to push forward this open source, or I guess as he likes to say, SAS, service-oriented software platform for computational photonics simulations. And I'll let him tell you more about that, and he's going to talk about that software and that product as I can say, in terms of computational electrodynamics. So with that, I'll hand it over to Dr. Oskooi.
Thank you very much, Amit, for the kind introduction and for the invitation to speak today. It's a great privilege to speak in front of such a distinguished group of scholars about my work. I'd like to first acknowledge my collaborators who made this work possible. Before I start telling you about my work, I'd like to begin by describing what my overall vision has been. This will set the stage for everything you'll hear in this presentation. Computational electromagnetism, despite immense progress over the years, is still not being used to its full capability in research and development, given the pervasiveness of low-cost, high-performance computing. Because Maxwell's equations can be solved on a computer to arbitrary precision, we should potentially make use of a computational laboratory to design a number of nanophotonic devices that push the boundaries of experimental research. A computational laboratory enabled by advanced simulation tools could make possible the discovery of new electromagnetic phenomena, the design of new kinds of optoelectronic devices. It could provide new insights into experiments. It could enable taking products from the lab to the marketplace quickly and efficiently, as well as being used as an educational platform for the teaching and learning of electromagnetism. The following is an outline of this presentation. I will begin with a brief overview of the finite difference time domain method for computational electromagnetism, and then I'll go on to summarize my two enhancements to the core capabilities of FDTD, involving subpixel smoothing of dielectric objects and absorbing boundary layers for inhomogeneous media. Then I'll describe our open source software tool, MEEP, which is an implementation of the FDTD method. The majority of this talk will be focused on new kinds of nanophotonic devices that were enabled by leveraging MEEP. These include light trapping in silicon thin films for enhanced solar cells, and light extraction from organic light-emitting diodes for energy-efficient displays and solid-state lighting. Finally, at the very end, I'd like to describe new opportunities for large-scale device design using high-performance computing in the public cloud. Finite difference time domain, FDTD, is a method to model Maxwell's equations on a discrete time and space grid using finite centered differences. FDTD has a rather long history dating back to the 1960s when the first attempts were made to solve Maxwell's equations on a computer. The key advantages of FDTD are its simplicity and its generality. The schematic on the left shows a Yee cell, the fundamental unit of the FDTD grid, showing where the different electric and magnetic fields are stored in order to accurately discretize Maxwell's equations. The image on the right shows an electrodynamic effect simulated using FDTD of a moving point charge with superluminal phase velocity emitting Cherenkov radiation. FDTD is rigorous and flexible enough to model a large variety of effects in different materials and geometries, and has two key advantages for device design. The first is that a short pulse produces a broadband spectral response in a single simulation. And the second is that parallelization enables simulation of large computational volumes, both of which you'll hear about later in my work. One of the main challenges to the accuracy of FDTD involves the issue of simulating discontinuous dielectric objects using the discrete grid. Suppose we want to model the circular-shaped object as shown on the left using the discrete grid in FDTD, which inevitably results in a kind of staircasing or pixelization effects as shown on the right. These discretization effects have a major impact on the accuracy of the simulations, as I will demonstrate. For simplicity, let's assign to each pixel the value of the dielectric at its center and perform a numerical experiment to investigate the errors due to discretization. Here are two figures showing data from FDTD simulations that are a plot of the relative error of the eigenmode of a periodic structure as a function of the resolution in the simulation. The figure on the left is for a one-dimensional multilayer stack, and the figure on the right for a two-dimensional array of cylindrical air rods in silicon. You will note that the data is sporadic, and more importantly, is showing only linear convergence with the resolution. Even though the finite differences used in the discretization of Maxwell's equations have second-order accuracy with respect to the resolution, the error is converging only linearly due to the field discontinuities at dielectric interfaces. This is similar to Gibbs phenomena in signal processing, where a discontinuous signal is being represented by a continuous sine series. We can eliminate the discontinuities by grayscaling, that is, assigning an average dielectric to each pixel. But the key question is how. Any kind of smoothing changes the geometry and may actually increase the error, even before the discretization. In fact, prior smoothing methods tended to make the error worse than no smoothing, and the convergence with the resolution was still only linear, as shown in the plot on the right, where the data for the no smoothing is shown in the hollow red circles and is compared to several previously published results that tend to have worse accuracy but are always showing linear convergence with the resolution. The approach to subpixel smoothing that we propose was based on an analytic criterion. Specifically, we pointed out that to reduce the errors and ensure second-order accuracy, the first-order effect of smoothing and changing the geometry should be zero. This requires correct perturbation theory near sharp boundaries with large index contrast that we had derived in previous work. Using this perturbation theory, we propose not a scalar form for the average dielectric, but a tensor, where the fields parallel to the dielectric interface are assigned the average dielectric, and the fields perpendicular the harmonic mean, consistent with the boundary conditions in Maxwell's equations. We then compared our subpixel smoothing method, shown as the blue squares, to those that were previously published, and demonstrated that not only did our method produce the lowest errors, but it finally restored the second-order accuracy of the underlying discretized equations. This accurate subpixel smoothing method enables the size of simulations to be significantly reduced. In this case, reducing the simulation time of this three-dimensional structure from 5 hours to just 15 minutes. Another unique feature of our accurate subpixel smoothing is that it enables the size and shape of geometric objects to be varied continuously without numerical artifacts being introduced into the simulation. The plot here shows the resonant frequency of a two-dimensional photonic crystal as a function of the size of the elliptical rods. The data in black shows the exact result, which is computed at a very high resolution. And the data points in red are for the no smoothing case. And you can see that as the size of the geometric object is increased, there are numerical artifacts that appear in the data. But our subpixel smoothing method preserves both the continuity of this change in the size of the geometric object, but also is quite accurate. This is important for enabling things like geometric optimization that I'll describe in my later work. Finally, we extended our subpixel smoothing method to handle anisotropic dielectrics by once again deriving the correct perturbation theory. We demonstrated that our subpixel smoothing method, shown as the red data points, produced the lowest errors and restored the second-order accuracy of the underlying discretized equations. The second major focus of my work on enhancing the core capabilities of FDTD involves the issue of simulating open boundaries. A typical photonic simulation involves the interaction of fields and objects, where the purpose of the boundaries of the computational volume are to absorb all outgoing waves without introducing numerical artifacts back into the simulation. The standard approach for absorbing boundary layers in computational electromagnetism is known as the perfectly matched layer, or PML, which is widely used in practice. Simulating open boundaries is an important engineering design problem. For example, when measuring the electromagnetic or acoustic wave scattering from objects. This figure shows an experimental setup to measure the radar cross-section of a tank placed within an anechoic chamber. The walls of the chamber are made of a radiation absorbent material that acts to minimize the reflections into the chamber. However, I showed that PMLs, which are the standard absorbing boundary layers used in computational electromagnetism, irrevocably fail when applied to inhomogeneous media, which therefore results in large numerical artifacts that significantly degrade the accuracy of simulations. Two examples of inhomogeneous media that are typically encountered in nanophotonic simulations are shown here. One is a PML. One is that for a waveguide that enters the PML region at an oblique angle, and the other is when a PML overlaps periodic media, for example, a Photonic-Crystal. Many nanophotonic devices are therefore challenging to simulate accurately using PMLs. We show that when PMLs fail, what remains is an adiabatic absorber, essentially a conductivity absorber for the electric and magnetic fields. We demonstrated the fundamental connection between the smoothness of the absorption profile and its reflections from the absorbing boundaries. And with this, showed that adiabatic absorbers can, with proper design, be used to reduce numerical artifacts in cases where PMLs fail. Based on this work, the absorbing regions can be made much smaller than before, thus reducing the size of simulations while also improving their accuracy. The figure here shows a plot of the field convergence, which is proportional to the reflections from the absorbing boundary layers as a function of the absorber length for 5 different absorption profiles. We incorporated the standard FDTD method, as well as our enhancements, including subpixel smoothing, adiabatic absorbers, and many others, into an open source software package known as MEEP. Since its public release in 2006, MEEP has become a popular tool in the photonics community, and we continue to actively maintain it. MEEP supports a large variety of simulations, some of which are shown here. MEEP can be used to compute the reflection and transmission spectra shown in the top left for a waveguide bend, as well as optical forces for 2 parallel waveguides as a function of their separation distance, properties of the resonant modes of waveguides and cavity systems, including quality factors, resonant frequencies, field profiles, as well as the local density of states, shown in the bottom right figure for a hollow metal box as a function of the size of its opening, and much more. One of the unique features of MEEP is that it is controlled using a scriptable interface, which enables things like parameter sweeps for geometric optimization. MEEP has a number of other unique features, including a frequency domain solver, even though it is a time domain tool, as well as some advanced signal processing that can be used to reduce the size of problems in important cases. MEEP's homepage provides extensive documentation into its features, tutorials that document different examples, installation instructions, as well as a place to download the source code, which I encourage you to check out at some point. Everything that I have described up until now is discussed in much more detail in a book that was published in 2013 and edited by myself and Professors Alan Taflov of Northwestern University and my graduate advisor, Professor Stephen Johnson at MIT. This book includes contributions from over 20 different researchers that span the latest in FDTD research. Now I'd like to turn to the applications in nanophotonics that were enabled by leveraging MEEP, starting with thin-film solar cells. Given my time constraints, I'm not going to try and convince you why solar cells are an important technology for energy generation. From an optics and photonics perspective, the key function of a solar cell is to trap as much sunlight as possible, which therefore leads to the following question. What is the maximum amount of solar radiation over the broadest range of frequencies and angles using the thinnest material possible? This problem was first addressed more than 30 years ago by Professor Eli Jablonowicz and his colleagues, who proposed that by applying a random surface texture to the front coating of an optically thick crystalline silicon solar cell, the light trapping could be significantly enhanced. This is based on the principle of scattering incident light rays into the index-guided modes of the high-index material, and has the remarkable property that it effectively doubles the optical path length of light. Because of its simplicity, it is widely used by the solar industry to create thick crystalline silicon solar cells which are 100 microns in thickness. More recent approaches to light trapping in thin films have involved photonic crystals and other nanostructures, which are based on an entirely different approach. Here, incident light is captured by a resonant mode of the nanostructure, which in principle can give rise to nearly 100% absorption, but only over a narrow bandwidth and select angles and polarizations. One of the unique features of resonance-based light trapping is that it can be realized in arbitrarily thin films, less than a micron in thickness, a fact which I shall return to later on. There have been many resonance-based approaches to light trapping over the years, some of which are shown here, including nanoparticles, plasmonics, photonic crystals, and nanowires. However, all resonances have the intrinsic limitation of narrow bandwidths and select angles and polarizations. The figure here, shown in blue, is the absorptivity spectra of a nanostructured silicon thin film, 500 nanometers in thickness, consisting of a periodic array of cylindrically shaped rods etched into the silicon, a photonic crystal absorber. For comparison, I also show the absorptivity spectra for an unpatterned film in red. We focus on the wavelength interval of 500 to 1100 nanometers, where the absorption coefficient of silicon is small, and thus the need for a light trapping design most significant. As you can see, the photonic crystal has very narrow peaks, which are indicative of the resonant modes in the structure, which are in contrast to the broad Fabry-Perot resonances of an unpatterned film. The percentages denote the light trapping efficiency, which is proportional to the area underneath each curve. The photonic crystal absorber is a significant improvement over the unpatterned film, But nevertheless, its performance depends very sensitively on the conditions of the incident light. How can these narrow peaks be broadened and the device made more robust? A simple and effective way to control the broadening of the peaks is through disorder. I investigated the effect of disorder on the absorptivity spectra by gradually increasing a perturbation parameter applied to the positions of the rods. I discovered that a partial amount of disorder maximizes the overall light trapping efficiency, as shown in figure C, but too much disorder leads to suboptimal light trapping. The key design principle then is to introduce as much disorder into the structure while preserving the resonance peaks without destroying them altogether. A broadened resonance, as you can see in figure C, is what I refer to as a quasi-resonance from now on. I also demonstrated rather predictably that an increasing amount of disorder tends to reduce the sensitivity of the absorption to the angle of the incoming light. The 4 figures here show the absorptivity spectra for 4 different Photonic-Crystal lattices with an increasing amount of disorder at 4 different angles of incidence, where the average is shown in the black curve, along with its standard deviation. As you can see, an increasing amount of disorder reduces the sensitivity of the absorption to the angle of the incoming light, both qualitatively and quantitatively in the standard deviation as it gets smaller with increasing disorder. I then proceeded to make an experimental demonstration of quasi-resonant absorption using the cleanroom facilities at Kyoto University. I used thin film deposition of a silver back reflector, followed by a 520 nanometer thick microcrystalline silicon active layer grown via plasma-enhanced chemical vapor deposition. I then performed electron beam lithography, followed by a dry etch and resist strip to form a photonic crystal lattice on the surface of the silicon film. I used MEEP to design the photonic crystal absorber to have a large number of resonant absorption peaks. By fixing the whole height and varying just the radius and the lattice periodicity, I designed the photonic crystal absorber to have a large number of resonances, as shown in the contour plot on the right. Here are the SEM images of my fabricated samples showing 4 different photonic crystal lattices with an increasing amount of disorder, along with a cross-section of the device. As you can see, there are imperfections in the profile of the etched holes, which is going to give rise to an intrinsic amount of peak broadening separate from the actual perturbation applied to the lattice. Here is the experimental absorptivity spectra shown in blue compared to the FDTD simulations. I found good agreement between the experimental data for a lattice with no disorder and the simulated results, which have a small amount of disorder, which is to be expected because of the fabrication imperfections that I showed you previously. Based on this good agreement, I was then able to use the simulations to explore the parasitic absorption in the rest of the device, which would not have been possible using an experimental approach alone. The figure at the bottom shows the absorptivity spectra computed using FDTD of the GZO layer, which is a little bit absorbing. I also demonstrated experimentally the peak broadening effect that I had predicted using the simulations. As you can see here, again, an increasing amount of disorder applied to the photonic crystal lattice tends to broaden the peaks. I also found good agreement between the experimental and the simulated absorptivity spectra for an unpatterned film, which suggests that my modeling was indeed accurate. Finally, I showed experimentally that an increasing amount of disorder reduces the sensitivity of the absorption to the angle of the incoming light. Again, here are 4 different absorptivity spectra for 4 different photonic crystal lattices measured at 4 different angles of incidence. As you can see, an increasing amount of disorder tends to reduce the sensitivity of the absorption to the angle of the incoming light. We can also demonstrate analytically why partial disorder increases the broadband light trapping by considering weak coupling of incident solar radiation to a single resonant mode of the photonic crystal, which has some amount of material absorption. The incident light couples at some rate to the photonic crystal mode 1 over tau rad, which in turn is absorbed at another rate, 1 over tau abs. Using just these two degrees of freedom, tau rad and tau abs, I can write down an analytic expression using coupled mode theory for the absorptivity, which is shown in the equation on the left. When these two rates are matched, 1 over tau rad equals 1 over tau ab, we get 100% absorption at the resonant frequency. By integrating this expression over all frequencies, we obtain a broadband quantity that's similar to the light trapping efficiency. Increasing disorder tends to reduce the lifetime of the mode, in effect making it easier for the light to leak out of the mode, which increases the broadband light trapping because the material absorption, tau abs, is mostly unaffected. In other words, as we apply disorder, tau rad goes down, the lifetime becomes smaller, but tau abs mostly remains unchanged, and therefore the broadband light trapping increases. Based on this, we can ask how to most effectively make use of partial disorder for light trapping enhancement in a thin film. The answer is to first maximize the number of resonances so that there's little bandwidth separation between the peaks, and then to add disorder. Here, we make use of the fact that resonances can be created in arbitrarily thin films, which means that instead of using a single slab, I can use a tandem arrangement to create an even larger number of resonances. This tandem arrangement of photonic crystal slabs is the optical analog of a multi-junction solar cell, which employs 3 or more different semiconductor materials to obtain broadband absorption. Here I'm using the same material, silicon, but structured in 2 different ways to obtain broadband absorption. The design strategy involves maximizing the number of resonances in the 2 slabs separately such that they add complementarily over the wideband spectrum, and then to apply partial disorder to each of the 2 slabs to maximize the number of resonances and increase the robustness of the light trapping. I used MEEP to perform the geometry optimization of the tandem photonic crystal slabs using the 7 geometric parameters that are shown here. Because of MEEP's accurate subpixel smoothing algorithm, I can vary these geometric objects continuously without numerical artifacts being introduced into the simulation. The figure on the left shows the absorptivity spectra for the optimized tandem photonic crystal slabs in blue. As you can see, there are a large number of resonances that span the entire broadband spectrum, where the absorption coefficient of silicon is small, and thus the need for light trapping design most relevant. It turns out that in this optimized tandem arrangement, the top slab was 700 nanometers thick, the bottom slab 300 nanometers, with roughly a 200 nanometer air gap between the 2. For comparison, I also plot the absorptivity spectra of a 1 micron thick Lambertian texture in red, as well as an unpatterned slab. Already, you can see that the optimized tandem slabs are a significant improvement over the Lambertian texture. The 2 figures on the right show the absorptivity spectra for the top and the bottom slabs separately, showing how the individual resonances add complementarily over the wideband spectrum. Now, we apply partial disorder to each of the 2 slabs separately to increase the light trapping even more and to improve the robustness of the device. The figure on the left shows a plot of the light trapping efficiency as a function of the disorder for the optimized tandem and single slabs. As you can see, a partial amount of disorder maximizes the light trapping efficiency, but too much disorder is suboptimal, just like what I had shown you previously. Now, for a given partially disordered tandem photonic crystal slab arrangement, I computed its absorptivity spectra at 6 different angles of incidence, averaged over both polarization, as shown in the figure on the right, with the average in black. As you can see, the tandem photonic crystal thin films absorption exceeds the Lambertian texture at nearly every wavelength and angle, with a total broadband light trapping efficiency that is almost 10% larger. This was the first demonstration of its kind to show super-Lambertian light trapping for a nanostructured silicon thin film over a broad bandwidth and angular range. Now I'd like to turn to displays and solid-state lighting. One of the key emerging technologies for energy-efficient displays and solid-state lighting are organic light-emitting diodes, or OLEDs. OLEDs generate light from organic molecules and are therefore thin, lightweight, and because of the disordered nature of films of these molecules, can be deposited in a variety of substrates, including flexible ones. As displays, OLEDs offer better color, higher contrast ratio, and a broader viewing angle compared to their LCD counterparts. And for lighting, OLEDs offer large area, low brightness sources. The schematic here shows a typical device structure of an OLED. The organic layers are grown on top of an ITO-coated glass substrate with a metal cathode, aluminum in this case, deposited in the final step. Electrons are injected from the aluminum cathode and holes from the ITO anode. These charge carriers then meet in the emissive layer of the organic where they form bound states called excitons, which spontaneously recombine to emit photons. Most of the light that's generated by the organic molecules does not in fact leave the device through the glass substrate. In fact, only about 20% of the total light that's generated actually leaves the device, which is a significant reduction of the device's energy efficiency. Light extraction is therefore a major area of research in OLEDs. The two figures here are a plot of the fraction of the total power in the OLED separated into its 3 components of glass, aluminum absorption, and organic ITO waveguide as a function of wavelength for white light emission spanning 400 nanometers to 800 nanometers. The average for each component over the entire wavelength interval is shown. The figure on the left is for dipoles that are oriented parallel to the layers, and the figure on the right for perpendicular ones. As you can see, the amount of power that's actually leaving the device through the glass is small, but it is almost negligible for the perpendicular dipoles, where losses due to the aluminum absorption are dominant. The only way to recover the power that's lost in the aluminum is to texture the cathode somehow. We can texture the cathode of white OLEDs using a lattice of nanoscale scatters similar to what's shown here in the schematic. The objective of the texture is to find a texture that enhances both the light extraction efficiency as well as the exciton radiative recombination rate, which are both necessary to increase the OLED's external quantum of efficiency. There are 3 key texture parameters: the lattice periodicity, A, the scatter morphology, which in this case are just simple hemispheres protruding from the aluminum cathode into the organic layers below, and the degree of disorder. Each of these 3 parameters plays an important role in the device performance. We can compute analytically the Surface-Plasmon modes that are excited at the metal surface, shown here in the blue curve. White light emission corresponds to only a subset of these modes, as shown in red. An effective cathode texture that can scatter out these Surface-Plasmon modes will have to have Fourier transforms that correspond to these Surface-Plasmon modes, which is shown in the schematic on the right. The annular ring shows where the Surface-Plasmon modes of the OLEDs lie, and the faint peaks, it's hard to see, correspond to the actual Fourier transform of a cathode texture corresponding to a lattice periodicity of 550 nanometers and a hemisphere radius of 40 nanometers. As long as there are spectral peaks in the cathode that correspond to those Surface-Plasmon modes, they can be used to scatter out the Surface-Plasmon modes and to recover the power that's lost due to the aluminum absorption. The figure on the left shows the fraction of the total power in the OLED for perpendicular dipoles for a cathode textured white OLED having a lattice periodicity of 550 nanometers, a hemisphere radius of 40 nanometers with no disorder. As you can see, the amount of light that's now reaching the glass is now 5 times what it was in the untextured device. However, more significantly, as shown in the figure on the right, the spontaneous emission enhancement rate of the excitons is significantly increased relative to the untextured cathode. This is particularly the case for the parallel dipoles because the texture breaks the planar symmetry that had prevented the Surface-Plasmon modes from coupling through the Surface-Plasmons. This can potentially be used to increase the overall device lifetime of the OLEDs. Here I'm showing you the light extraction efficiency for a blue OLED, where you can see in the 2 plots in the bottom row that the light extraction for a blue OLED is much more uniform and much more significant because the texture is targeting a very narrow bandwidth compared to the broad bandwidth spectrum of the white OLED. Again, the enhanced radiative recombination rate could be used potentially to improve the overall lifetime of these blue OLEDs, which is a significant limitation of their practical use. Finally, I discovered that a partial amount of disorder can be used to enhance the light extraction efficiency of these OLEDs. The figures here, shown in the black, are the surface height function of the OLED, along with a one-dimensional cross-section of its Fourier transform shown on the right. As you can see, an increasing amount of partial disorder in the texture broadens slightly the spectral peaks, which can be used to scatter out an even larger number of Surface-Plasmon modes. But too much disorder gives rise to a very weak scattering effect, very similar to the work on light trapping efficiency that I had shown previously. These were very large simulations that that required almost 200 cores. That took about 8 hours to run. I had to use the Texas Advanced Computing Center's Stampede cluster through an allocation provided by the National Science Foundation's XSEED program. And so significant computational resources were required to generate these results because this is kind of based on a Monte Carlo-like method where because of the disorder in the device, you have to do many different iterations and get a statistical average to show reliable results. Okay, now let me turn to the last section where I'd like to just briefly describe new opportunities for large-scale device design using high-performance computing in the public cloud. Using simulations in research and development has typically required expensive commercial software licenses and significant high-performance computing resources. But now, the combination of advanced open-source simulation software and low-cost, scalable, high-performance computing in the cloud lowers the barrier to entry. As some of you may be aware, we now have access to significant computational capability through resources provided by commercial vendors like Amazon and Google, where virtual machines can be rented for literally pennies per hour. And what this infinite level of computing provides are new possibilities to do large-scale device design. But to really leverage this vast computational resource that's now available, we believe that it's important to have access to open source simulation software that has no restraints on its use, that can be quickly deployed in the cloud to leverage the scalable resource. And we believe that there are going to be a lot more kinds of large-scale device design enabled by the combination of open source simulation tools as well as commercial public cloud high-performance computing. Now let me summarize my presentation. I described my enhancements to the core capabilities of FDTD involving subpixel smoothing of dielectric objects, as well as absorbing boundary layers for inhomogeneous media. I then described our open source software tool MEEP, which is an implementation of the FDTD method that includes our enhancements. I then showed how I leveraged MEEP to enable new kinds of nanophotonic devices for light trapping in silicon-thin films for enhanced solar cells, as well as light extraction for energy-efficient displays and solid-state lighting using OLEDs. Finally, I gave you a brief glimpse on new opportunities for large-scale device design using high-performance computing in the public cloud that leverages open-source simulation software. I really believe that the future of computational photonics promises many more interesting things to come. Thank you very much.
Well, thanks for that wonderful presentation, some really exciting work, and I'll open up to questions from the audience. Yes, Jerry.